Quantum mechanics began with several discoveries. Among the most known and most famous are the Michael Faraday's cathode ray, the black body radiation statement, and a mathematical equation that could describe many quantum phenomena. It's called the Schrödinger equation. It is based on a bunch of probabilities, on a distribution of probabilities. It doesn't give an exact result, but just an approximation of where we can expect the result to be. This equation nowadays is as important to quantum mechanics as Newton's second law is to classical mechanics. Nevertheless, it was very contradicted and criticized by a person named Albert Einstein.
In 1935, Einstein and Podolsky published an article called "Can Quantum Mechanics Description of Physical Reality Be Considered Complete?" In it, they negated the proposals of Niels Bohr in the field of quantum mechanics. And what does Niels Bohr said? Well, he said that measurement changed everything in our physical environment. This means that before we take a measurement, the nature of the objects is uncertain. For example, if we are studying a particle, the position of that particle is not determined until we make that measurement. And once we make that measurement, the particle has to choose a place to be. And we force the particle to be in a certain place, and the nature is no longer undetermined. We have determined the position of that particle. We want to take a visual of what I just said. Here we have our experiment, and we have a number of possibilities where our particle can be. This is before the experiment. Then we make our measurement, and after that the particle had to choose one of these possibilities, and it had to remain in that place because we have already determined the value of that position. A physical example of what Niels Bohr said can be made with a muon. In this case we have a muon that is neutral. This is a particle, and then in a certain point in time it decays into two other particles. Because the initial muon has a neutral charge or a neutral angular momentum, we can say that the first particle, let's say that it has a 1/2 positive spin, and the other, because this one has a plus sign, this has to has a negative sign. So if we add both of them, this will give a neutral muon. But what Bohr said is that these two numbers are undetermined until we make our measurement. So this would be the case before making the measurement. So if I take this particle and I see that it has a positive spin, then that will mean that the other one has a negative spin. Now, looking at this same example, but from the point of view of Einstein, he said that these numbers are already determined before taking our measurement. So if I take the measurement and I see that this has a positive sign, that will mean this one has a negative sign. But these numbers were already there before I took a measurement to discover it. This is what Newton said in the field of quantum mechanics, that everything in nature is determined. So let's think a little about this example that we just saw. We have one particle here, and another one here, and when I determine the spin of this one, then this one is also determined. That will mean that information from this side is traveling faster than light to this side, because they are determined in the exact same moment. So what does this mean? That the theory of local realism that say that nothing can move faster than light is being violated. So what does Einstein say to this? He said, well, there are certain hidden variables in our experiment, whether in the particle, in the environment, that are determining the characteristic that we are studying. And we do not know that hidden variable, but they are still making their work there. They are determining what we are already measuring. So this will mean that there is no uncertainty in the characteristic of nature. They are already determine characteristics, and we do not decide which one will be when do we take the
So,
measurement.
experiments based on Bell's theorem started in the 60s. However, it was not until a team led by Alan Aspect performed a set of experiments that the violation of Bell's inequalities became evident. In their setup, photons were emitted by a calcium-40 cascade source towards which a frequent and selective pair of photons were incident. The wavelengths of the photons emitted by the calcium source lighten the visible spectrum, and their quantum correlation relied on polarization. Photons were fired at opposite directions, where dichotomic polarizers capable of being rotated measured the polarization of the photons. Their experimental results dictated a deviation of about 80%, the maximum possible deviation predictable by quantum mechanics. There have been several more recent experiments in Allen aspects, every time with use of improved experimental setup and equipment, and each one of them has strengthened further the fact that there are no hidden local variables involved in quantum systems. What does this mean to physics? Physicists on the side of realism and locality expected this entanglement phenomena to be a consequence of the mathematical formalism used to describe quantum mechanics. However, Bell's inequalities violation through experimentation means that nature actually does in fact work non-locally. But in what way? We know that measuring one part of the system defines what the measurement of the other part will be, independently of the distance that separates these two elements. Quantum entanglement is non-local. However, it does not violate causality. An observer measuring the property of one of the entangled elements cannot decide what the outcome of the experiment will be, and therefore cannot transmit a message to an arbitrarily distant point in space where the other entangled particle is.
Now we will talk about Bell's inequalities, which arise from the question, what would happen if hidden variables actually existed? Bell's inequalities hold when two hypotheses are met. The first one is that our two entangled particles, each one will depend on a function of a hidden variable. And these functions will be independent of each other, and according to Einstein's hypothesis of hidden variables. These functions also have to be local, which means that they cannot communicate faster than the speed of light. Because we will be doing experiments related with spin, we can also get only two results from the measurements we make in a certain direction A, which are positive or negative for both functions. And according to these experiments, if we have the same direction, then the measurements will be opposite, because the particles are entangled and initially the system did not have any angular momentum. We will also define the probability function P of A and B, which is the probability of our apparatus A measuring a positive spin and the probability of our apparatus B measuring a positive spin, both in the same experiment. What does quantum mechanics say about this probability? Well, it has to meet this condition about the 1/2 of the sine, and this is the angle that is made between the two measurement directions. We can do a simple test to verify this. Let's say we have two opposite measurement directions, and in the first one we get spin up, and because the system is entangled, the second one we expect to have spin down. Therefore, the condition is met. The other option is that we have a spin down in this measurement apparatus, and therefore we will have a spin up in this measurement apparatus. Therefore, we can expect that the condition does not hold. So we have probability of 1/2. So it agrees with our experiment. Now, consider the following experiment to test the EPR conditions. Remember, The EPR conditions assume that there is no superposition, and therefore the state of the particles are defined just after our system is entangled. So we can have only a limited number of states. Here, in this experiment, we will have a total of n pairs of entangled particles. We will have a measuring apparatus 1 for particle 1 and a measuring apparatus 2 for particle 2. And each apparatus will have 3 different measurement directions. Here are the possible ways the system can have their particles. For example, consider the case when in the apparatus 1, A, B, and C can measure the positive direction. Then, so that experimental conditions are met, apparatus 2 will always have to measure negative, negative, and negative for the 3 directions. We want to analyze these probability conditions. Here, what this is telling us is that what is the probability of finding that a measurement in A in our system, in our apparatus 1, correlates with a positive measurement in the direction B in the apparatus 2. Let's see. Positive A, we have N1, N2, N3, and 4. When this is the number of particles that you have in this state. So N1, N2, N3, and 4. And for B positive in the second apparatus, we have 1 and 2. You see being this one, N3 and N4. Therefore, the probability is N3 plus N4 over N. We can repeat this for AC and for CB. And here we have the different results. So you can corroborate with this table. Now, let's see what inequality we can construct with the results we just got. We can see that N3 plus N4 is less than N3 plus N4 plus N7 plus N2. This is kind of obvious because if we subtract N3 plus N4 from both sides, we will be left with N7 plus N2 be greater than 0. So we have this inequality that we know it's true and divide by N. Let's see the results we had before. And N3 plus N4 over N is this. And the same can be said about these two sums. This is one of Bell's inequalities that you can obtain from a more general form, which is this one. And these are relevant because these inequalities relate your quantum interpretation with actual experimental results. And this is the significance of Bell's discoveries. Now we will analyze what does quantum mechanics says about these predictions. Now, remember what we said before about the probability function when interpreted with quantum mechanics, the formalism? Oh, it's here. We just substitute each probability with the angle that our measuring apparatus have. But what happened when we consider this configuration that we are presenting here? This is direction A, direction B, and direction C, and the angle they make. If we substitute these angles into this equation, we have this equation. But with further analysis and considering the obvious fact that sine of theta is approximately equal to theta, where it's not angles, we have this inequality, which is obviously wrong because 1/2 is not less than 1/4. What this is telling us is, so what does this tell us? If local realism is true, then Bell's inequalities hold. But experiments show that Bell's inequalities do not hold. Thus, we can conclude that local realism is not a compatible theory. But wait, you might be saying, what about the relationship we got with quantum mechanics? Does this mean that if Bell's inequalities are wrong, then quantum mechanics or the interpretation that we have is true? Well, not really. You see, there are many interpretations about quantum theory that agree with the results we got before, and they are different. For example, we have non-local realist theories. we have many words interpretations. We have non-local and non-realist theories. So there's all these different interpretations that all agree with the results we just got. So the only conclusions the Bell's inequality gives us is that we cannot have a local and a realist theory at the same time. But you might be saying, wait, what? Non-local. So that means that most of the interpretations we have are non-local. Does that mean that relativity is wrong? Again, not really. Because in quantum mechanics, there is a very funny phenomenon. Non-local theories do not necessarily violate the causality relations that we have with general relativity. This is because even though the information is passed faster than the speed of light, you cannot send any message using that information, that faster than light communication. This is known as the no communication theory. Imagine this. There is Alice with one apparatus and there is Bob with one apparatus. The experiment involves an entangled pair, but because Alice and Bob are 20 light years apart, Alice changes the apparatus direction and Bob changes the apparatus direction. So Alice can't know Bob's direction. And at the end, the results that Alice will get is that according to her direction, 50% of the spins give her a spin up and 50% spin down. And the same for Bob. So you really can't know about entangled pair until you compare directions, that Alice and Bob get together and say, oh well, I had this direction in these experiments, and Alice says I had these directions in these experiments. So in order to get an information communication, Alice and Bob will have to meet. But once they do, then, well, we won't have any local non-local communication. So we're still safe, and we still don't have faster than light communication. Damn it.